Hi, Terry Allen, Inventing Guitar Mathematics. In this lecture, I'm summarizing my systematic study of Beatles guitar music intelligence and drawing conclusions about the guitar and music in general. I'm here in the Music Cognitive Laboratory, which is the oldest cognitive laboratory for investigating machine intelligence in the world, although many feel that music lags behind the cognitive laboratory for chess. And the goal of guitar music intelligence is to learn guitar faster and better by an algorithm that directs experiments. So we call the Beatles guitar music intelligence black box intelligence because we can't see what the Beatles did on guitar. We don't have any direct instruction, and so we have to use the music in the recording to try and deduce the behavior of the guitar. The important method that I use is tablature writing, because writing tablature is almost the same thing as playing guitar. So if we understand the rules for rewriting tablature in different tuning, key, and intonation parameters, then we understand the theory of guitar. It might seem that every guitarist plays in their own idiosyncratic way, as if there are no rules. But in fact, guitarists play things using the same schemes. And you know this if you play in standard tuning, because you're probably using the key of E or G or C or D or A, but you're not very likely to use the key of E flat or D flat. So if you hear Hendrix playing blues in E flat, you might assume, if you're looking at it from the standpoint of standard tuning, that he's actually got his guitar intonated a little bit low, and so you just kind of nudge that key to a more probable key of E. And that shows that the guitar is a probability field in which the chance of having any key is not 1/12, but certain keys are favored over other keys, and that's called a distribution, a harmonic distribution of musical keys. So what we're doing is we're using the guitar music learning algorithm tree to direct our search for the guitar music we want to play. Because the problem is there's so many ways to write tablature for music in a recording that it's easy to become confused and end up practicing the wrong form of guitar, hoping that repetition will make it correct. So the tactics we use in the strategy of learning music tend to concentrate on repetition and advancing to more difficult forms over time. But on guitar, what we want is we want to find the simplest way to play the music, because there's no point in having a more difficult way of playing the same music. And we want to avoid the problem of thinking that we know how the music goes, and later on, and sometimes much later on, finding that that isn't how the music goes at all, and having to relearn the guitar. Now, in the cognitive laboratory for guitar, we have two machines that we use for learning guitar music. The first is the guitar itself, and the second is the audio recording. So the phonograph was the first machine besides the guitar that was used for learning guitar. But still today, even with these devices that can slow down guitar music at constant pitch, there's still a problem of understanding how do we get from the pitch to the guitar. Because every tuning, every key on the guitar, and every guitar intonation level uses the same set of pitch values. So when we say guitarists learn by ear, it's not clear then how they would learn music differently in one tuning from another. And it's the way of changing between tunings and keys that clarifies what the general principle of the theory of music is. The thing that we're interested in music is the comprehension principle. We can define music as any sweet, pleasing, or expressive sound that's understood as having meaning. But then the meaning of music is understood naturally without any special education. And so the problem is that the music, we all like to think that music is mathematical. And the evidence is clear that we have these operations that are mathematical, but the problem is that ordinary mathematics is sub-analytical on the guitar, because we can't use the pitch to understand the behavior of the guitar, because the guitar behavior is the same at every pitch level. So these tunings have the same structure up to the point of naming the notes. So open D and open E are the same tuning, but open D is intonated with the lowest note on the guitar, D, and open E is intonated with the lowest note, E. Now you may think that they have the same tonality, but what happens is if you're comparing it to a record, the observed key in the record will be seen in a different way according to the level of the guitar intonation. So this creates a very confusing problem in which it seems like the computational complexity of guitar is overwhelming. The possibilities are so high that we can never figure out how the music actually goes in the record. But that's not correct. In fact, what happens is the tablature that you end up with after you apply all of the rewriting rules is always the same regardless of how badly you write the first working sentence of tablature. In other words, you can transcribe Beatles guitar music in any tuning or key that you want. And then if you work through the system systematically rewriting the tablature in better and better ways, you always end up on the same leaf of the tree. So the guitar music algorithm learning tree has for roots the guitar tuning, and it has for stems a bag of tricks that are created by the tuning that lead to the leaves. And the leaves of the tree are the terminal pages of tablature, the ones that you want to learn the first time because they're the best ones. So the comprehension principle in music means that we comprehend a string of notes according to a harmonic property that is universal for every note. So people write about how music is composed by a large number of rules, this bag of tricks that we have in harmony. But in fact, music is mathematically simple, and so it has to have a simple principle by which we understand music. And what we want to understand is the property of the total expression. The tonal expression is every possible element, relation, and function in music, the sum total of all these things. And tonality is a grand object. It's not simply a pitch that can only go up or down. There's a monotonic function of one variable of frequency, because then we can explain why different guitar tunings have different tonality. Now the funny thing is, the observer cannot tell when guitar tuning changes, and they have the impression that every guitar tuning sounds the same. But if they did even a small number of experiments, they would realize that, in fact, the tonality, the tonal expression of each guitar tuning is different. So for example, if you had a guitarist who was, say, 4 guitarists, and each one of them is using one of the big 4 guitar tunings that the Beatles use, and you had them play music and you listened to the 4 of them without knowing the tuning, you would quickly learn to recognize which guitarist is which one, because the tuning that they're using in some is a very characteristic picture. So there's no question that we can identify the tuning that's used in a record. The only problem is whether we have an adequate sample. So if we got notes that, go over the whole neck of the guitar, there's not going to be any question about the tuning. When we have a song that has only a couple of chords and a few riffs, then you have a mathematical problem trying to decide, okay, which tuning in this situation is best. But the general idea that the guitar tuning is, that guitar music carries an image of the guitar tuning with it that you can recover from the record, is a sound mathematical principle. So the way that we establish the comprehension principle in music is, first of all, we have a set. We have a set of notes, and then we define membership in the harmonic set, which are the set of notes which have the harmonic property. And what we want is, we want one property, one simple law that accounts for all of the findings. Now, to represent the tuning, we have a number with 6 intervals, or actually 5 intervals, and 1 0. The 0 represents the position of the first string. So in the mathematic textbook, they usually represent the vector in 6 dimensions would have like commas. They'd have 6 coordinates separated by commas and surrounded by a parenthesis. But the commas and the parentheses add nothing. So I represent these numbers simply as a digital serial number that identifies the tuning in a characteristic way. So the tuning is a vector with 6 coordinates, and so is any state on the guitar that comes from the tuning. So the tuning is a distinguished state by which we know every other state on the guitar. For example, an E chord in standard tuning would be a vector 0, 2, 2, 1, 0, 0. And in the same way, we can represent vectors which change the tuning or the key by a 6-digit number. So in the top number here, 2, 0, 0, 0, 0, is a number that will change the tuning because it doesn't affect each string equally. It only affects the bottom string. Add 2 to the bass string, you change the tuning from standard to drop D tuning. Now, that instruction to add 2 frets to every note on the bottom string is in fact not enough to change to drop D. It's the algebraic part of the operation. But once you do that, you still have to rewrite the tablature for the drop D tuning. And the reason is because sometimes when you add 2 to a chord or a scale, you get something that's unplayable. And you have to make a substitution. So in fact, the adding 2 frets to change to drop D from standard is just a memory aid. And it's not enough to allow you to play in drop D. So if you take your repertoire that you know in standard tuning and you change it to drop D, what will happen is that it takes a substantial amount of work, and you'll be left with some things that don't really transfer very well from standard to drop D. But you'll also find that there's some things in drop D that cannot be played in standard tuning. Now the second number here, -2, -2, -2, -2, -2, is the key changing vector. It doesn't change the tuning, but it affects every string on the guitar by an equal amount, and that changes the key. So this would lower the key of E to the key of D. Now in the bottom number, but have the 0 in the first digit because the 2 and the -2 cancel out and make 0. And then I have 0, -2 for every other digit. So this is a vector that changes both the tuning and the key at the same time. And that's very important because it shows how these vectors can add. And it shows that they're already axiomatized in mathematics. Okay? We already know how this operation works. It seems to be just ordinary mathematics, but that's the trick of the comprehension principle, because if you start with a defined set and then you create membership, you understand music because it has a membership in the set of all harmonic sets. Then you make the music into just ordinary math. Okay, everything seems to work just like real numbers, and there's no indication that the mathematics of music is defined by a special improper law that doesn't apply to the rest of mathematics. So if you look on the Music and Mathematic page of the American Mathematical Society, what you'll find is they're very enamored with the association between music and mathematics. But everything that they write about music is like fake math. It's like there's no theorem, there's no definition, as though we can understand music in an ordinary mathematic way, and we don't need to define the theorems of algebra because we know they already apply. But in fact, what's happening is there is a simple equation. This is the grand equation of music theory, which tells us everything that we need to know about music. And what it says is that music is the sum of the 12-tone set, which adds up to 1. And that's 1 as in the one that's equivalent to true or false. So this equation, which I've never seen anywhere in the literature, is well known to mathematics as a Borel set, and it creates a distribution of harmonic elements. And the interesting thing about this distribution is it's dynamic. It's not empirical. Everyone thinks that the rules of harmony are empirical because they're easy to see and measure and explain. But the problem is that these rules of harmony were not evident in the beginning and became evident only after a large number of experiments. So in the dynamic theory of music, what happens is that there's a central tendency for the harmonic set, and that under a large number of experiments, you end up with this terminal state. So that's what happens with the derivation of tablature. Is if you rewrite the tablature enough times, you're going to end up with the best possible tablature, and trying to apply more rewriting rules will not generate any more new forms. So this equation is can be represented in other ways, and usually found in the literature as the expression P equals log 2F. The pitch equals log 2 frequency. And that's kind of a funny equation because on the other hand, we have this thing where we think that the pitch is equal to the frequency. So we say, like the middle C is 256 hertz. We say that middle C is equal to the frequency, but then we have this other expression that says it's equal to log 2 frequency. So how can they both be true? And the fact is that because of the octave, which identifies the point 0 and the point 1, these two equations have a one-to-one relation, point for point. And so they can be substituted. P equals the frequency, pitch equals frequency, can be substituted for the pitch equals log 2 frequency expression. And that's equivalent to a situation where every A is equal to every A squared. That's what the octave says. It says that A is equal to 1 over A, or A equals A squared. And the mathematician David Hilbert pointed out that if you have a system in which every A equals A squared, then you already have a system for defining the rules of consonance and dissonance. Now, consonance and dissonance are a great unsolved mathematic problem of science. It's been considered since the time of Pythagoras, and then there's a huge corpus of literature about mathematics that is highly confused, where every author has their own theory about what's going on, and they all seem to agree that music is somehow subjective and beyond mathematics. And this is a pleasing anthropomorphic vision of music because it's something that man made that defies mathematic explanation. And so we're kind of still holding on to this idea that there are golden ratios in the music of the spheres that Ptolemy talked about. He thought the planets were in these golden ratios, the same ones that explain the golden ratios of music. But the problem is, it's not ratios, it's intervals. And the ratios work out perfectly well for analysis, just like the real analysis of frequency works out very well. But the problem is that they're sub-analytic. They can't explain consonance and dissonance, which can only be explained in a discrete fashion. So going back to my fundamental equation of music, what is remarkable about this sum, this fact that the 12 tones add up to exactly 1, is that we can substitute the integral for the sum. In other words, this is the smallest instructional set we have, 12. Any set 12 or larger in music is big enough to contain all of music theory. Contains every note, every interval, every scale, every chord, every key within that 12-step unit. So this is an example of a system where you have the smallest instructional set, and there are no sets that are smaller. And everything comes from the 12-tone set. Now, one of the things that became very confusing was that Pythagoras indicated that the harmonic overtones are simple multiples of the fundamental. And then looking at the string, you have this computer with a push-button multiplication system. So you push down on the string in the middle and you multiply that frequency by 2. And if you push down at 1/3 of the string where it meets 2/3 of the string, you multiply by 3. And so you have these overtones that are simple multiples that go octave, and then the second and third overtones. And the interesting thing about those overtones is each one is individually coherent. But in total, the natural overtones don't add up to 1. They don't make a coherent system because as you go higher and higher with the overtones, it gets harder and harder to get that overtone. So by the overtone that divides the string into 4 parts is pretty good, but not quite right on. And then the next overtone is kind of off the musical scale, and it's not as loud. And then the other overtones just seem to just sort of disappear in an ethereal way where they're not adding up to a fixed point limit. So in mathematical analysis, the standard method is to identify a distribution, a probability distribution or a harmonic distribution, and then show how that distribution is obtained by integration against a point. And that's why it's significant that the guitar tuning is a point-wise limit that defines the entire tuning language. So the membership question is the most important part of theory, because if we can identify what tuning membership a song has, then a trained guitarist knows how to write the music. Okay, so if I tell you the tuning, that's enough, that's necessary and sufficient intelligence for you to learn the song. But it still could take a lot of work. It still could take years. So if you have in addition the key on the guitar, that saves time. And also if you know the level of the intonation of the guitar, saves time. So in this study, I followed a procedure in which I would first guess the tuning, then I would determine inside that tuning which was the best key for the song, and then I would use the best tuning and the best key to determine how the guitar is intonated to match the record. And this procedure is critical to avoid the error of taking the pitch and trying to place it directly on the guitar, say in a standard tuning and in the observed key, because that will almost invariably result in a missense error. A missense error in which the pitch of the tablature is correct. The chords, the scales, everything matches the record, but the tablature is completely wrong. So this is what you have in the Beatles' complete score, is the transcribers only knew standard tuning. They transcribed everything in standard tuning and intonation. Because if you say, well, standard tuning is the notes E, A, D, G, B, E, what you really mean is standard tuning and intonation. So it's a kind of a monotonic view of the Beatles guitar. And what I like about the Beatles complete scores is the music is accurately transcribed. Okay, the chord symbols and the notes in the musical score are very accurate, but the tablature is almost completely wrong. And you can't use the tablature in the official publication to learn Beatles guitar without some additional information, which is not apparent to the music user. So guitar behavior in recordings is left adjoint to minimal realization as functors between these two machines that we have, the guitar, which is a discrete non-linear machine, and the phonograph record, which is a linear machine where the pitch can only rise and fall. So guitar realization theory is then a classical theory of intelligence expressed in contemporary algebra in a way which reveals the inner structure of harmony and suggests generalizations about the expression of music. An adjunction between regular sets and the finite acceptor states on guitar follows. And the fact that there are a small number of acceptor states, which are these commonly known tunings, shows how highly convergent the guitar is, because there are no new tunings that have been introduced recently And it's highly unlikely that a tuning that is not already known will enter common use. And the reason for that is we've performed a large number of experiments on guitar, and we know which tunings are best. And there are approximately 10 tunings in the category of the best possible tunings. It's certainly less than 100 good tunings, and it kind of depends whether you want to count the slack key tunings and so forth, which is a limitation in this study because I didn't really consider that slack keys were very likely except for the All Across the Universe song, which is in the Honolulu Blue A9 tuning. But otherwise, the Beatles are using fairly standard, well-known tunings. So I collected 251 examples of Beatle music, which included their original songs and also their covers of other people's songs. And I was able to analyze 220 of them for tuning, key, and intonation. And so this pie graph is the spectral image of the tunings that I observed. You could think of this as being a spectrum. If I presented it as a histogram, it would look more like a frequency spectrum. But I like the pie graph, and I think of it as an image of the leaves on the guitar tuning tree. That's a little bit different than the guitar music learning tree because the guitar tuning tree has tunings for leaves rather than tablature. And the pie chart is useful in showing the harmonic distribution of tunings in two ways. First, it shows an order of tunings because every set in music has an order with the first and the last element and a place for every element between. So that means if you take a group of tablature that's written for the same music, you can rank them in order from best to worst. And so the fact that the guitar music is rankable set is very important because it allows you to realize which set is best. Now, I want to talk about recognition and realization because those are the elements of tablature comprehension. And recognition is a language membership test. So a Turing machine, we can say, is a machine that we can ask, is this sentence, this tablature sentence, written in your theory? And the Turing machine will compute and it will halt and it will answer yes or no. So let's perform an experiment where we say you have some tablature for a Beatles song, but we lost the tuning. It's an unknown tablature. We don't know what tuning was used to write the tablature. So we look at the numbers. We can't tell the key. We can't recognize any chords. It's just fret numbers written on string lines. Okay? But what we can do is we can play the tablature in every possible tuning in serial order. And then when we get to the tuning that was used to write the tablature, all of a sudden we recognize, oh, that's Lucy in the Sky with Diamonds. So that proves, that's mathematical proof of which tuning was used to write the tablature. So the guitar is an instrument that can recognize what language the tablature is written in. And that's a very straightforward, obvious experiment with a profound implication, because if the guitar can recognize when tablature is written in a specific tuning, it can be used as an instrument in general to analyze all tablature senses to see if they're true or false in the context of the tuning grammar. So the tuning grammar is one of these dynamic things where if you have the tuning for the Beatles song, it's still hard to figure out the grammar. But there isn't anything else but the tuning that's necessary to learn the grammar. And so the question is, how do we get from the tuning intervals to the grammar? Now, looking at these numbers, here we have 10 tunings that I observed in 220 Beatles songs. And they line up in such a way that have them all here listed. And first thing I want to do is just talk about patterns in these numbers, because that's what mathematics is about, is looking for patterns in numbers and developing theories about what the pattern comes from. So we're looking at these are the best possible tunings for Beatles, and we want to look for patterns that they have in common. So one pattern is they almost all begin with either 057 or 075. So what that means is the first three strings going from bottom up add up to 12. So that we have an octave, whatever notes on the bass string will also be on the fourth string from the top. And so the tunings that are 057 are in the family called G. The G, G major tuning, G minor tuning, drop G. And the tunings that begin 075 are in the D family. They would be like D, open D major, open D minor, Dad, Gad, and double drop D. And another interesting pattern in these tunings is that the totals sum up to 24 in all but 2 or 3 examples. So that means that you have the same note on the bottom string and the top string in octaves. So there's something about the best tunings where you like to have octave notes on the first, fourth, and sixth string. What happens here is that all of these tunings are related by at least 3 strings in common. And so you can get from one tuning to another in one step by changing no more than 3 strings at a time. Now when the tuning changes by the smallest possible increment, you have to basically relearn everything. And it's kind of funny because, like, say between open G and open G minor, you have 5 strings that are same, and then you have this one string, the second string is tuned to B in open G and B flat in open G minor, and it creates a completely different tonal expression. Even though all those strings are the same, it has a different sound, and it takes a long time to learn, if you know open G, to learn open G minor. Now there's kind of a way of measuring, like what I think is it takes usually 3 to 5 years to learn a new tuning, maybe longer. But you know, some people are smarter and can learn faster. So one measure of tablature information is a page of tablature. So I use tablature manuscript paper that has 9 staves on it with 4 bars for each stave. So that's 36 bars. And what I find is if you write a page of tablature for a song, you will learn a lot. And if you write, say, 3 pages, you'll learn almost everything that you can at your skill level. Now, you keep coming back to these things over and over, and you make small changes. But if you've written, say, 12 bars 9 different ways, you're going to learn a lot about the tablature. If you write 100 pages of tablature for one tuning, you'll know it's substantially well, but it probably takes more like 1,000 pages to really master. And what's satisfying about these optimal tunings, the really good tunings like open G minor, open D minor, and then the equivalent ones which are open A minor, and open E and open E minor. They have this quality where you can really learn a lot. You can develop a high level of skill and find it very interesting as you go further and further. So tablature has the property of consistency like music, in which it can be difficult to understand, but the more you write tablature, the better you get at it. And so as you change from one tuning to another, you learn different techniques, changing from to different tunings, and going back and forth between tunings, you hone your knowledge of the guitar in a general way. Now in this illustration, I'm showing a pie graph that shows the guitar keys as they're distributed in the 4 most important tunings. And it's clear that the Beatles knew these 4 most important tunings from the very beginning, from their earliest recordings. Whereas the tunings like drop D, double drop D, and dad-gad were accessory tunings that came into the canon of Beatles guitar music in the mid-60s. And they don't appear in the earliest songs. And they also show a tendency to use just the 0 key, the key that the tuning is named after. So, for example, if you are playing an open D and you play every song in D, that shows that you haven't really mastered the tuning because you're just making use of the simplest key. And so what I think is really surprising is some of the keys that the Beatles use are really original. For example, the key of F in open D minor is very surprising key. It's great fun to play, and it's sort of not surprising because after all, D minor and F are relative keys. But what is more surprising about open D minor is the key of B flat, in the same way that the key of E flat in open G minor is a very useful key. And the useful keys are a kind of a signature that identifies a tuning. So if you see somebody, or excuse me, if you hear somebody who's playing guitar and they're using the keys of E, C, G, or sometimes D, sometimes A, then you're going to think that they're playing in standard tuning. But if you saw somebody who was playing in the key of E flat, and B flat, and G minor, then you would think, well, this is probably in open G minor. And I must say, for a long time I had a kind of prejudice against open G minor because I think it's the most difficult tuning, but it's also one of the most interesting tunings and very important in early rock and roll. So these key charts show the distribution of keys, and what I've done here is I've normalized the guitar key. So instead of calling the key F in open D minor, I'm calling it the 3 key. That's the key where the tonic forms a bar on the 3rd fret. And so that way I recognize that the key of F in open D minor is the same guitar key as the key of G in open G minor. And so this is a very confusing aspect of the guitar intonation, because you think, well, if the tuning goes up or down, I don't really care because I don't have to learn anything different. And so the tonality of the music is the same. And that way you're deceived by the fact that the guitar intonation is critical because it determines the key that matches the record. So the experiment in which you have unknown tablature and you are able to recognize the tuning is extremely important because it shows the guitar is intelligent. And the realization is the other part of comprehension. And what realization means is that you're going to find the best tuning eventually. You're going to realize the best tuning if you repeatedly write the tablature in different tunings. And what happens is you think, wow, there's a lot of different tunings and keys to try, and I'm never going to get through all of them. But what happens is there's an efficient search algorithm. And what the efficient search algorithm says is you don't have to try every tuning and key to know which one is best. So let's look at this problem of recognizing the unknown tablature. And imagine that you're playing the tablature for Lucy in the Sky in a tuning with, say, 2 or 3 bad strings. But there's enough correct notes that you recognize, say, oh, this tablature is Lucy in the Sky. And every time the note falls on this string, it's a bad note and it's off by 2 frets. So then you go, once you recognize the song, even with several bad strings, you go directly from that to the correct tuning, and you don't have to try all of the other tunings. And so this is what happens in the problem of finding the tuning for a record where the tuning is unknown. You don't have to try every single one because you can see that certain tunings are just not going to work out. And you get this kind of thing where things sort of click into place as you get the intonation of one string right. You get a better tablature and you say, oh wow, that must be how they play it. But it's still possible that there's another better tablature out there that you haven't found. So it's for sure that people can tell what guitar tunings the Beatles are using. And the only question in my study is whether I've done enough experiments to justify my conclusions. So a measure of the resolution of the image is how many tunings you consider. So in the Beatles' complete score, published by Hal Leonard in 1992, they only consider one tuning, and the tablature is correct if that tuning, that one tuning, is the tuning the Beatles used for every song. But it's impossible to believe that the Beatles were these guitar experts who love guitar and they only used one tuning. That doesn't make any sense, and they're under pressure to write more songs. So naturally they're going to return to these tunings and try and work them for everything they have. And that's why these songs, 76 of the songs appear to be in the open D minor or E minor tuning and rarely intonated at C. And then you have 52 tunings that were in the open D major type of tuning, also intonated as open E. And you have 43 songs in the open G style tuning, or open A. And then you have 23 songs in the open G minor tuning. And so the open D minor type of tuning is clearly the Beatles' favorite. It's the first music copyright that they wrote, and it's the last, Free as a Bird or Real Love, which were actually written by Lennon after the Beatles broke up, but later made into Beatles recordings. And it is really a good tuning So the guitar is intonated about 2/3 of the case at the D level, and about 1/3 of the case is at the E level, and then there's an occasional intonation at C, like in Blue Jay Way. And the intonation at C is kind of uncanny because it throws you off. When the tuning goes up, it's easier to recognize it's the same tuning, but when it goes down, sort of disappearing off of the nut of the guitar, it really creates a kind of a unrecognizable form. And so, they came up with this weird tuning that they think applies to Blue Jay Way, when it's more easily explained with open D. And so what we're looking for here is we're looking for the guitar arrangement that takes the least memory. That's how we define what the best tuning is. It's the one that takes the least memory, and we can't necessarily say that that's the tuning the Beatles use, but what we can say is that's the best one to learn first. So what we're looking for the Beatles guitar music intelligence is a paradigm. And the paradigm is an illustrative form that's useful for understanding the guitar and learning the guitar parts. And so, in a way, it's not a surprise that the Beatles are using open G and open D and open G minor and open D minor as their big tunings, because these tunings are common in guitar in general. So it's possible that in this study, this merely reflects my preference for these tunings, because I knew all of these tunings before I started this systematic study. And I also have been studying Beatles guitars since they came out in the 60s. I was already playing guitar, and I knew these chords A minor, C, and G, and I thought, wow, the Beatles are using some kind of special chords. They don't sound like these ones that I learned in my guitar lesson. And then you see this sheet music comes out, they're using the chords A minor, C, and G, and so you kind of have to surrender, well, that must be how it goes. And I know a lot of people have argued with me that insist that the Beatles use only standard tuning, and you say, well, how do you know? And they say, well, because I've played them and I see the published music. And so that's kind of a strange situation I'm in, because the work that I'm doing is reproducible and it's measurable in its precision, but in order to understand what I'm talking about, you're going to have to learn these guitar parts in the tuning and key that I suggest. And the only way that you can prove that I'm wrong is by learning the guitar parts and then finding a better key or tuning. And there's a chance you can do that. I think the best chance would probably be in Dadgad, because I only found one example of Dadgad tuning, and that tuning has a strong association with the British Isles, and I just tend to think that the Beatles must have known Dadgad and used it for more than one song. I also think I might be pushing drop G. I have like 4 examples of drop G tuning, which in my older notebooks was much larger. I had, at one point, I thought, like half the songs are in standard tuning and half the songs are in drop D with a couple of drop G tunings, and that reflected pretty much my knowledge of the tuning. And I must say here that I have like, I think 7 songs in standard tuning, and those are songs where I tried every single tuning I could to get out of using standard tuning, and like Rocky Raccoon, you just have to finally admit that it's played in standard tuning. So I think I'm probably underrepresenting standard tuning, but I think what I've done is I've formed a fuzzy image of Beatles guitar music intelligence, which is a marked improvement over the published version. Now this is a kind of a joke on mathematicians because there's this huge body of literature about music and mathematics, and not one single mathematician actually thinks that music is a formal mathematic language. This clear tablature is a formal language. Its letters are numbers, and they're formed sentences according to the rules of the tuning. So it's a formal language, and what's happened is in the long marriage of music and mathematics, it's always seemed that somehow music is not a true member of the mathematic family. But in fact, what's happened is mathematics has failed to understand music. And if we go back to the days of Pythagoras, Euclid, and Ptolemy, they began the experiments that led to guitar theory on the first programmable digital scientific instrument, which is the canon. The canon is a string that's stretched over a soundboard, and on the soundboard, diagrams are drawn with a compass and a ruler to establish mathematical proofs about the nature of pitch. So mathematicians considered that music theory was subject to mathematic proof. And that's what happens in tablature, because a mathematic proof is simply a finite number of steps that comes to a conclusion. So in the tablature derivation, you write the tablature the first time any way you want, doesn't matter how badly you do it, and then you rewrite it a finite number of times and you get to the best tablature, and you've proved mathematically that's the best way to play it on guitar. So when you recognize the tuning of Lucy in the Sky and the unknown tablature, that's a mathematic proof. Now what happened to music is somewhere in the Middle Ages, they became confused about what was the law of music. Because if there is an axiom of music, and the Wikipedia says music theory has no axiomatic foundation in modern mathematics, which is absurd, because if there is an axiom, it has to be an axiom that's generally recognized and already known, accepted without proof. And that is clearly the octave. The octave is the one true note. So when you talk about intonation on the guitar, it's kind of confusing because I'm talking about intonation of the guitar system as a whole, and that gets mixed up with the system of intonating the guitar note, which is determined by the position of the bridge and adjusted for the thickness of the string and so forth. But the problem developed in the Middle Ages with the consideration of tempering the keyboard. And the guitar doesn't require tempering because every string is the same length. So the bridge, you have to adjust it a little bit for the thickness of the strings. But basically the frets march up the guitar fretboard according to the rule, the ratio is the 12th root of 2, so all 12 of them sum up to 1. And that rule is not tempered. And so when the problem of tempering the keyboard came up, because each string on the piano is a different length, and it requires an incremental adjustment to obtain a scale that's in key in tune throughout all of the keys, that created some confusion about the mathematic nature of music, because if notes are integerized, then it seems like they're not determined by one law. And that's a mathematical mistake, because the important thing that makes music decidable is that you have notes that are connected by intervals, and they don't leave anything out in the real line. So you have only the finitely many connected points, and that's the smallest instructional set. So music is mathematically determined with or without tempering of the scale. It doesn't matter how this the 12 tones are arranged as long as all of the 12 tones add up to exactly 1. And nowhere is this mathematical joke clearer than in the theory of the vibrating string. So Euler came up with an equation for the vibrating string, which basically looks like a Fourier sum. You have the sum of these different trigonometric functions that represent the different modes, and he added up all the modes. And at the time, he apparently thought that if we have a series like the natural overtones, where each successive term is smaller, that series will converge on 1. But Cantor later showed that's not true, that these are transcendental functions, and even though each term is getting smaller and smaller and smaller, it doesn't converge on anything. Whereas the characteristic of tablature in the guitar music learning tree is that it converges on the leaves. So Euler heard that Bach had made a tempered keyboard in which the key and the pitch seemed to be interchangeable to him. So he imagined this plane in which a note could move in 2 directions. It could change by pitch or it could change by key. And then if you close that plane, you get a donut. And so we have these musicologists like Dimitri Timokoso and Guerno Mazzola, who think that music moves along a donut, on the surface of a donut, and that the key and the pitch are independently determined. But that's absurd. Obviously, the key is defined by a tonal center, which is a pitch. So the key and the pitch have to be defined by the same fundamental. And so Euler's mistake was that he didn't realize what Mobius found out 30 years later or so, that there's only 2 possibilities for a theory. It's either a donut or a sphere. And Euler just made the wrong choice, because the sphere has the advantage that it shrinks down to 1 point, which is the fundamental, and it also has the advantage that it's required for an algorithm. So if music is an algorithm, what it means is the tone can move by changing the pitch, it can move by changing the key, and then it can move in a 3rd logical direction in which the change is both in the pitch and the key at the same time. So this is kind of like the surface of the Earth, where the latitude can change in 2 directions. You have 2 great circles that go around and change latitude, which would be like the musical key and the pitch. And then you have this other circle, the equator, where the pitch or the latitude doesn't change, but a tonal movement occurs. So there's a tremendous irony in this, because Euler was the one who first gave us the importance of the path in mathematics, but he made a mistake in music when he thought that the path was only 2-fold, because the path has to be 3-fold. And the joke here is that music theory is simple, and there can be only one mathematic explanation for it. So whether I have it right or not is not so much the issue, because there's only one way that this can work. And it has to be a sphere and not a torus. So one of the reasons why I did this study was because I wanted to show how Beatles guitar music intelligence grows on trees. Okay, and the idea of growing means that you construct the tree with a series of experiments that you perform on guitar. And those experiments operating the guitar as a finite state machine are the only way that you can understand how the mathematics work. So this is why tablature has always been the bad boy, the bad score that's rejected as the offspring of music and mathematics, because neither music or mathematics understands how tablature works. So that what's interesting about music theory is the closed model. And what the closed model means is that we have the principle of comprehension defined within a universe where nothing can occur in music that takes you outside of the universe. And so what's important about music theory is the rules for closure. And if you talk about that algebraic closure operator of the guitar tuning, people tend to freak out. But it's just those intervals, so you have like 5, 7, 5, 3, 4, that's open G minor. And those intervals are the star of the tuning. So the tuning point and all the lines that pass through that point is called a star. And so the tuning language is not exactly the tuning itself, it's the clean star of the tuning point. And Paul Kleen was an American mathematician who worked on Turing machines and demonstrated how they can be used intuitively. So often mathematical machines like the guitar can be operated in an intuitive way, as the Beatles did, because they didn't use any mathematics in the overt sense. And they're operating the machine according to the mathematical rules of guitar, but they're not thinking about them as being anything unusual. They just think, okay, if I have a note on the top string and I want to play it on the second string, that's 5 frets apart. And so it's just this simple kind of algebra. But what happens is it's a very sophisticated kind of algebra. And the important thing is that some tunings are very, very good, whereas the vast majority of tunings are useless junk that no one ever wants to experiment with. So the idea that music is dynamically determined, it follows directly from the idea that you have the musical key and the structure of the musical key is preserved in every tuning. So you have a situation where whatever is true for music is also true for guitar, and whatever is true for guitar is also true for music. It's a duality, but knowing music by itself never leads to learning guitar.